What's up guys, this is Masi. Welcome to my channel. In this video I want to talk about acidic and basic properties of salts. So first of all I want to talk about what is salt and what does it mean when we are talking about salt. And after that I'm going to talk about salts that produce neutral solutions, and then salts that produce basic solution, and then at the end we have salts that produce acidic solutions. And in each part I will give you some examples and you will figure out how to find out if the salt showing basic condition or acidic condition or neutral condition. So let's start with the definition of salt. Salt is simply another name for ionic compound. So when we are talking about ions, cations and anions together, it means that we are talking about salt. When a salt dissolves in water, we assume that it breaks up into its ions, which is going to be cations and anions, and these ions can behave as acids and bases. So let's see, when do we have salts that produce neutral solutions. So recall that the conjugate base of a strong acid has virtually no affinity for protons in water. This is why strong acids completely dissociate in aqueous solution. Thus, when an ion such as chloride or nitrate are placed in water, they don't combine with proton and have no effect on the pH. So basically, as you know, strong acids, when they dissociate completely. And on the other hand, we have their conjugate base, and the conjugate base is going to be extremely weak and they don't have any affinity to react again with the proton to accept the proton. So they have completely no affinity to get that one and have no effect on the pH. On the other hand, cations such as K plus and Na plus, or potassium and sodium ion, from strong bases, as you know, such as KOH or NaOH. So these ions have no affinity for proton as well, nor they can produce proton. So they are too weak and have no effect on the pH of an aqueous solution. So salts that consist of the cations of strong bases and the anions of strong acids have no effect on proton concentration when they dissolve in water. This means that aqueous solutions of salts such as KCl, NaCl, NaNO3, and KNO3 are completely neutral and the pH is 7. So they don't perform acidic, they don't perform basic, and they are completely neutral. So now I want to talk about salts that produce basic solutions. Assume that we are talking about the aqueous solution of sodium acetate, NaC2H3O2. The major species are sodium ion, Na+, acetate, and water. What are the acid-base properties of each component? As you know, the sodium ion has neither acid nor basic properties because that's the cation of strong base. So as we learned in previous slide, sodium ion doesn't have any affinity to react with proton, and that's why it doesn't have any effect on the pH. On the other hand, we have acetate ion, and it's a conjugate base of acetic acid, and acetic acid is the weak acid. We know all the organic acids are categorized as weak acids. So acetate is a conjugate base of acetic acid, and this means that acetate has a significant affinity for the proton and it is a base. So finally, water is a weakly amphoteric substance. So the first one, which is sodium, has no effect. Now it's completely neutral. Acetate is the conjugate base of a weak acid, and water, which is a weakly amphoteric substance. So the pH of this solution will be determined by the acetate ion. Since acetate is the base, it will react with the best proton donor available. And who is the proton donor? it is going to be the water molecule. Water molecule is the only source of protons, and the reaction between the acetate ion and water is like this. Acetate plus water is going to give you acetic acid and hydroxide. Note that this reaction, which yields a base solution, involves a base reacting with water to produce hydroxide ion and a conjugate acid. We have defined Kb as an equilibrium constant for such reaction. So those reactions that produce hydroxide, we define Kb. The value of Ka for acetic acid is well known as 1.8 times 10 to the power of negative 5, but how can we find out the value of Kb? The answer lies in the relationship among Ka and Kb and also Kw. Kw is autoionization constant of water. So note that when the expression for Ka for acetic acid is multiplied by the expression for Kb, the result will be Kw. So as you see here, Ka times Kb, when we do this multiplication and division, it results in proton times concentration of proton times concentration of hydroxide, which will be equal to Kw. So Ka times Kb is always equals to Kw. So whenever we have Ka, we can find out the value of Kb very easily by dividing Kw by Ka. So for acetic acid, Kw is always constant at 25 degrees, so it's 1 times 10 to the power of negative 14, and Ka is 1.8 times 10 to the power of negative 5, so Kb will be 5.6 times 10 to the power of negative 10. So to review this part, for any salt whose cation has neutral properties such as sodium ion or potassium ion and whose anion is the conjugate base of a weak acid, the aqueous solution will be basic. Let's have an example. We want to find out the pH of a salt of a weak acid. Calculate the pH of a 0.3 molar NaF solution, and the Ka value or dissociation constant of HF is 7.2 times 10 to the power of negative 4. So we have NaF and we have HF. So NaF is the ionic compound. The major species in solution are Na+, sodium ion, fluoride, and water molecule. Since HF is a weak acid, the fluoride ion must have a significant affinity for protons. And the dominant reaction will be fluoride plus water is going to give us HF plus hydroxide ion. So Kb can be defined as concentration of HF times concentration of hydroxide divided by concentration of fluoride. And we can find out the value of Kb using the Kw divided by Ka. That will give us the value of Kb. Kw is always constant at 25 degrees and Ka was given in here. So 1 times 10 to the power of negative 14 divided by 7.2 times 10 to the power of negative 4 will be 1.4 times 10 to the power of negative 11. And then we need to construct an ice table. We have the initial concentration of fluoride, which is 0.3. We have it here, the concentration of NaF, 0.3. And on the other side, we have HF and hydroxide, initially 0. Then change will be negative x for the fluoride and positive x and positive x for HF and hydroxide respectively. So the equilibrium will be 0.3 minus x, and on the other hand we have 0 plus x, which is going to be x, and the same thing for hydroxide. So Kb can be defined as, we can substitute all these numbers. For HF we can put x, hydroxide x, and for fluoride concentration we can put 0.3 minus x. So we can simplify 0.3 minus x by just 0.3 if we neglect that x, if we assume x is much smaller than 0.3, so we can have it as simplified form. So x will be 2 times 10 to the power of negative 6. That x is the hydroxide concentration. And then after that we can find the POH and then pH. pH is 14 minus POH, which is going to be in this case 8.31. So now let's talk about the last part, which will be salts that produce acidic solutions. In general, salts in which the anion is not a base and the cation is the conjugate acid of a weak base produce acidic solution. Some salts produce acidic solutions when dissolved in water. For example, when solid NH4Cl, which is ammonium chloride, is dissolved in water, we can produce ammonium ion, and chloride ion is going to be present, with ammonium ion behaving as a weak acid. So weak acid is going to produce ammonia and proton. On the other hand, the chloride ion having virtually no affinity for proton in water. Why? Because chloride ion is the conjugate base of HCl, and HCl is the very strong acid, so Cl- is going to be extremely weak conjugate base. So chloride doesn't affect the pH of the solution, but ammonium ion does. Let's have an example. Salts as weak acids. We want to calculate the pH of a 0.1 molar ammonium chloride solution, and the Kb value for ammonia is 1.8 times 10 to the power of negative 5. So what kind of species or ions are present? We have ammonium ion, chloride, and water. So ammonium ion is gonna produce ammonia and proton, so Ka will be ammonia times concentration of ammonia times concentration of proton divided by concentration of ammonium ion. Kb is given, so using this formula we can find Ka. We had it before, so Ka will be 5.6 times 10 to the power of negative 10. So we construct the ice table again. So we have ammonium ion, the initial concentration is 0.1, change negative x, and equilibrium we have 0.1 minus x. On the other hand, initially 0 and plus x for the change, so equilibrium we have x and x. We just sub it there, simplify it, so Ka will be 7.5 times 10 to the power of negative 6. So since this is the concentration of proton, we can use it to find the value of pH, which is 5.13 in this case. So let's see some examples. Here we want to predict whether an aqueous solution of each of these salts will be acidic, basic, or neutral. Here we have ammonium acetate. The ions in solution are ammonium ion and acetate. As we mentioned previously, Ka of ammonium ion is 5.6 times 10 to the power of negative 10, and Kb for acetate is 5.6 times 10 to the power of negative 10. Thus, Ka for ammonium ion is equal to Kb for acetate. So the solution will be neutral, which is pH is going to be 7. So although we have ammonium ion, which is willing to lose or give proton, and on the other hand we have acetate, which it has affinity to get proton, but since they have the same Ka and Kb value, the solution will be neutral. Next example, we want to figure out NH4Cn if it's acidic, basic, or neutral. The solution we have ammonium ion and cyanide ions. Ka for ammonium ion is 5.6 times 10 to the power of negative 10, and Kb for cyanide is 1.6 times 10 to the power of negative 5. So as you see here, Kb of cyanide is much larger than Ka of ammonium ion, so Cn minus is a much stronger base than ammonium ion in an acid. So the solution will be basic. Next one, predict whether an aqueous solution of each of the following salts will be acidic, basic, or neutral. So here we have Al2SO43. The solution will contain AlH2O6 3+ and SO42 minus ions. Ka of aluminum hydrate is 1.4 times 10 to the power of negative 5, and Kb for sulfate is 1.2 times 10 to the power of negative 2. So we have the Kb. Ka actually is Ka2 for sulfuric acid is 1.2 times 10 to the power of negative 2. So Kb will be 10 to the power of negative 14 divided by Ka, which is going to be 8.3 times 10 to the power of negative 13. So Ka of aluminum is much greater and much larger than Kb for sulfate. So it means that the solution is acidic. So we can have a summary here. Summary of acidic and basic properties of various types of salts. The first one, the type of salt is cation is from strong base and anion is from strong acid. For example, we have KCl, KNO3, NaCl, NaNO3. Comment is going to be neither acts as an acid or a base, so it's going to be neutral as we had it earlier, because the conjugates, they have no affinity to lose or to get the proton. Second one is going to be cation is from strong base and anion is from weak acid. So since cation is from strong base, cation has no effect on pH because it is very weak. But the anion, since it's from weak acid, is going to be a strong conjugate base. So acts as a base, and the pH of solution will be basic. For example, we have sodium acetate, KCN, and NaF. The third one is going to be cation is conjugate acid of weak base, and anion is from strong acid. So since anion is from a strong acid, it has no effect on pH, but cation is conjugate acid of weak base, so it's going to show acidic condition. So the solution is going to be acidic, like ammonium chloride and ammonium nitrate. The fourth one, cation is conjugate acid of weak base, and anion is conjugate base of weak acid. In this case, cation acts as an acid and anion acts as a base. For example, we have ammonium acetate and ammonium cyanide. So depending on the Ka and Kb value, it can be acidic, it can be basic, or it can be neutral, like some of the examples we had earlier. And the last one, when cation is highly charged metal ion and anion is from strong acid. So hydrated cation acts as an acid and anion has no effect on pH. So we will have an acidic solution like Al, NO3 and FeCl3. So this is going to be the acidic and basic properties of salts. I hope you enjoyed this video. Please leave me a comment if you have any question and I'll get back to you as soon as possible. If you found this video useful, please like it. You can also subscribe to this channel to have access to many other videos regarding math and chemistry and physics. Thank you for watching and have a great day.